Hello everyone, hope you guys are doing well. On this series, I'll be talking about chemical bonding, and the first thing is going to be the ionic bonding. So before we move ahead, I want to remind what is the chemical bonding. Chemical bonding is a lasting attraction between atoms, ions and molecules. Okay, so but we need to get a stable octet to get that chemical bonding. Once you get the stable octet, you get chemical bond. What is octet? Octa means 8, and octet rule means that you need to have 8 electrons in the last shell. That means that 1, 2, 3, 4, 5, 6, 7, 8. So in the last shell, you need to have 8 electrons. That's what it means. So sodium is given in here for us, and then chlorine. If you write the electronic configuration, you will see that first shell you have 2 electrons, second shell you have 8, third shell you have 1, because 1s2, 2s2, 2p6, and 3s1. So this is first shell, this is second, and this is third. So you do the same for chlorine, you would see that you have 2, 8, 7. We know that we need to get octet rule. That means that we need to lose this electron, and this guy, chlorine, gotta take that electron. And once it takes, it becomes negatively charged, the chlorine, and sodium becomes positively charged. Because he lost electron, this guy gained electron. And then they make this chemical bond where sodium is positive, chlorine is negative. We know that positive and negative attract each other. This is called because of electrostatic force. So why we have this electron losing and gaining? Okay, losing and gaining. It is because of the electronegativity. We know that electronegativity means ability to attract. That's why when you have a high electronegative, such as fluorine in here has an electronegativity of 3.98, and lithium here we have 0.98. So because fluorine has a higher electronegativity, fluorine will take this electron and make himself negative, and lithium will lose that electron and becomes positive. Low electronegativity loses, and higher electronegativity gains electron. So they make positive and negative, and they attract each other, and this happens commonly between metals and nonmetals. Metal and nonmetal, as sodium is metal and chlorine is nonmetal. But it can also happen between polyatomic ions, which we have covered with you guys. And this is ammonia, and we have nitrate. Because ammonia is positive, nitrate is negative, they make ionic bonding. Okay, ionic bonding, you need to get positive and negative. Positive means losing, and negative means gaining. So now we're going to go through some of the cations. Cations, we know that it is positive charged ion. So the first group elements, they always have the 1 electron in the last shell. They lose that electron. That's why they become positive 1 charge. Okay, they have a valency of 1. And the second group, because it has 2 electrons in the last shell, they lose it to get octet, and then they become positive 2 charged. And the third group has got 3 electrons in the last shell, loses those 3 electrons, make it plus 3. So this guy's got 3 valency, this guy's have valency of 2. But the D block elements, you can have a different types of ions. For example, iron, you see here, we got positive 2 and we got also positive 3. For example, in here, you got copper plus 1 and plus 2. Okay, depending with whom he binds, it can make +2 or +1. So now we're going to go into anions, which is negatively charged. And then 17 groups, you guys need to know this by heart. They are always -1. Fluorine, chlorine, bromine, iodine. And oxygen is -2 because he needs 2 electrons. 17 group just needs 1 electron to complete octet. Complete octet rule. And then 15th group is nitrogen, is becoming -3 because it needs 3 electrons to complete octet. And then polyatomic ions for -1, we know we got nitrate, for example. -2, we got carbonate. And then -3, we got phosphate. Okay. And then this is the way we write it down. For example, we know that aluminum is +3 and sulfur is -2. So sulfur is also here, sulfate. And then aluminum, you see, it's +3, right? And sulfate is -2. So -2 here, this 2 comes into the bottom like this, and then 3 goes to here, and then aluminum sulfate looks like this. Okay, crisscross, you do go like this. For example, sodium +1, and then carbonate is -2. So -2 comes here and +1 comes here, so it becomes sodium carbonate, just like this. Solid state comes in 2 shapes. One is amorphous, one is crystals. Amorphous is where you have, as you see, it's chaotic placement. You can see irregular, right? There is no structure. And this is the example is Play-Doh or plastilin in Russian. So you can easily reshape these guys because they have no structure in the solid state. But we have crystals where they have a very nice and structured way with them. And this structure makes these guys really hard. But Play-Doh is, you see, is not hard at all. Not hard. It's more of a soft side. And when you have a crystal, you make it hard because all of the structures support each other, all the molecules. So, and right now in solid states, the reason we're talking about crystals because ionic molecules in solid states, they make a crystallic shape, or they call it crystal lattice. And this is how it looks like. For example, sodium and chloride. You see here, this is sodium and this is chloride. This is negative and this is plus. Because positive and negative attract each other, this is positive and then negative, positive. They attract each other. They make this very organized shape. Okay, and this is how they make the crystal shape. And that's why they become hard. Okay, so now over here they're going over and saying that large ordered structures, you see ordered structures formed by intramolecular electrostatic attraction between oppositely charged ions. Now we're going to talk about intra versus inter in next video, and so don't worry about this for now. Just understand that intra means we got positive and negative within the same molecules. So now we're going to summarize the properties of ionic crystals. So as you see, they are hard. We talked about the shape. It's because of the crystallic. And the reason they are hard in solid state, just remember this. Now, they have a high melting and boiling temperatures. The reason is, it is again the crystallic shape. You see, they are very much attracted to each other in here, and that's why you need a lot of energy to break them down. That's why their melting point and boiling point will be high. They are soluble in water and other polar substances. We will talk about the polar ones in the next minutes. So when you throw the sodium inside the water, you know that the table salt, like let's say we have a water, you add it inside salt, because it dissolves inside. You see positive and negative, they stop attracting each other, they dissolve. Now they are in solved state, they go from here to here. So these guys are soluble in water, they do not conduct electricity. The reason is they do not conduct electricity, again, has to do with the shape. You see, in a solid state, they are very attracted and they are structured shape. So there is no free ion or electron. You need free ions and electrons to conduct electricity. Because you don't have any free ions in crystallic shape, they do not conduct electricity in a solid state. But when you melt them down, they become liquid, right? They conduct electricity. Or when you dissolve it, as it's happened in here, they conduct electricity, but not in solid state. At high temperatures, or when dissolved, intramolecular forces that keep ions together are broken, so ions can move. I explained you here. So when you dissolve it inside the water, the forces, intramolecular forces, they are gone. And the same thing, when you melt it down, they will be gone as well. They become liquid. That's how they conduct electricity. Okay? So polar compounds, we're going to talk about them, but I just wanted you guys to take a look at this. So sodium chloride, you see the melting point? Very high temperatures. You can't do it at home. These are all ionic bonds. Now this time we're going to talk about the covalent bonding. This is number 2. So we have talked about this, that in order to gain stability, you need to get octet rule. Octet means 8 electrons in the last shell. So once you get 8 electrons, you become like noble gases, as they are shown in here. The last group, they all have octet rule completed. So let's review the ionic bonding. So ionic bonding happens between metal and non-metal. Electron transfer from one atom to another. We already talked about this. I got sodium and chloride, where sodium gave it electron from the last shelf. Sodium become positive and chlorine is negative. They attract each other, they make ionic bonding. Now I will show you guys how to do Lewis dot cross diagram. Lewis dot and cross diagram. But we're going to do it for magnesium fluoride. So magnesium fluoride we have, let's write it down. So for magnesium we got 12 proton number, and fluoride we got 9. So if you write the electronic configuration, this guy will be 1s2, 2s2, 2p6, and 3s2. And then fluoride, it'll be 1s2, 2s2, 2p5. So we got 2, 8 on the second shell, and the third shell we got 2 electrons. First shell we got 2, and then second shell we got 7 electrons. So now I'm gonna write them down. I have 1 magnesium and 2 fluorides. So I got 1 magnesium, first shell, I got second and third. So second and third. I've got fluoride, I got 1 and 2, and then another fluoride, 1 and 2. And now I'm gonna put the dots. This is gonna be dot, and this are gonna be cross. So dot on magnesium 1, 2, first shell, second shell 1, 2, 3, 4, 5, 6, 7, 8. And then last shell we got 1 and 2. Fluorine I have 1, 2 on the first shell, and then second shell 1, 2, 3, 4, 5, 6, and 7. Sorry, I should have put. So on fluorine, I'm gonna put the cross. Okay, so 1 and 2, and the second shell we got 7, 1, 2, 3, 4, 5, 6, and 7, and then next 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got first shell we got 2, and second shell we got 7 electrons. They are both all 0 charge. So now we need to get octet rule. Octet rule. That means that I need to have 8 electrons in the last shell. So 8 electrons in the last shell. So if I lose these 2 electrons, so one is going to be going into this fluorine. So one of my electrons is going to come here, and the other one is going to come here. So what it will make is going to be looking like this. So now magnesium, because he lost both of his electrons, magnesium have only 2 shells left. And that 2 shells are going to be looking like this. Magnesium 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8. And then fluorine, right now, that's how it's looking like. So I got fluorine, so 1 and second shell, and then another fluorine, 1 and second shell. So now I have crosses 1, 2, and then 1, 2, 3, 4, 5, 6, and 7. But the last one is going to be dot because he got it from magnesium, and the same thing 1 and 2 on fluorine, and then I have 1 common as a gift, and then 1, 2, 3, 4, 5, 6, and 7. So now if you count it, now we got 8 electrons here, we got 8 electrons here, and 8 electrons here. And magnesium become positive 2 charge because he lost 2 electrons. Fluorine gained 1 each, is going to become negative and negative, meaning negative 1 and negative 1. So negative 1 and negative 1 here. Oops, and so negative 1 charge, I'm just going to write it in a nice way. So negative 1 and negative 1. And now they start attracting each other, and this attraction happens. So I'm just going to remove this ones. Now this is how their shape is looking like. So I'm just going to put it in bracket, and this one in bracket as well. So this is the Lewis cross dot diagram for magnesium fluoride. Now we're going to talk about the covalent bonding. So covalent bonding happens between non-metal and non-metal. The electronegativity difference between them is going to be less than 1.8. So electronegativity, we talked about it, that it is the ability to attract electron. So electronegativity. If the electronegativity difference, so I put this sign for the difference is less than 1.8, it is covalent. But when electronegativity difference is more than 1.8, it is going to be ionic. So electronegativity difference, when it is below 1.8, they share electron. Do you remember we said in ionic you lose or gain? But this time they share. And there are two types of covalent bond. One is polar and the other one is non-polar. So the polar ones, they have the electronegativity difference different than the non-polar ones. And I'm just going to show you the example and then we do a calculation together. So polar ones are these guys, hydrochloric acid, water, and etc. And non-polar ones, you see oxygen on oxygen, nitrogen, and chloride. They made a non-polar ones. So now this is the one that we have a hydrogen molecule. You see, we got H and H. Now, electronegativity, we talked about that is the attraction. So when it is less than 1.8, it becomes covalent. When it is in between, if the electronegativity difference is more than 0.5 and less than 1.8, it is polar. So this is polar. But when it is less than 0.5, then this is nonpolar. And then, as you see, the larger the difference it gets, the greater the polarity of the bond. Polarity is the same thing as, you guys know that we have North Pole and South Pole in the Earth, right? So polarity means that differentiation, when you have a lot of difference. So hydrochloric acid. Let's look at the electronegativity of chlor. You see we got here 3.16, and over here it is shown as 3.0, which is pretty close, and hydrogen is 2.2 from the P table, and then we got here 2.1. So the difference between them, the electronegativity difference, is 0.9 approximately. When it is more than 0.5, we said that it is polar, right? So polar. So polarity happens this way. So you have hydrogen and chloride made a bond, right? You have chlorine, which is more electronegative. You see, we have higher electronegativity, which means that two electrons that they are sharing are going closer to chlorine, because chlorine is more electronegative. So that's how we make this guy a little negative charge, partial negative, and then this guy become partially positive, because chlorine attracts those electrons closer to himself. He doesn't take it all. They share electron, but chlorine just drags them closer to himself. That's how we make the polarity. We have a North Pole and South Pole, and then we have positively charged part and negatively charged part. This is called polar. Now I'm going to show you another examples in the next slides, but now let's consider the covalent bonding. What it is, covalent bond. We talked about that it is sharing of electrons. So I have here fluorine molecule. It comes as in like this, diatomic. Diatomic means they come in two. So I got fluorine in the last shell. We got fluorine has how many electrons? 7. Fluorine has 9 atomic numbers, so it is 1s2, 2s2, 2p5. So we got 7 electrons in the last shell, and they're shown in here 1, 2, 3, 4, 5, 6, 7. And then these two together, you see, they share these electrons. They share electrons. Now let's count the electrons around each fluorine. So 1, 2, 3, 4, 5, 6, 7, 8. Now you have octet. 1, 2, 3, 4, 5, 6, 7, 8. So around this guy we have 8 too. So octet rule completed. And this happened with sharing. And this is non-polar covalent. You know why? Because when I take the electronegativity difference, I have here fluorine and fluorine. They have the same electronegativity. If you look from the P table, the fluorine electronegativity is 3.98. So 3.98 minus 3.98 will be 0. So it will be nonpolar. Nonpolar. So now let's look at the water. We have here oxygen. Oxygen has how many electrons? Oxygen got proton number 8, which is 1s2, 2s2, 2p4. So we got 6 electrons in the last shell, right? So 1, 2, 3, 4, 5, 6. They are here. Hydrogen is 1s. 1s1. We got 1 electron. So 1 in here and 1 here. So now they share electron. The reason they share is because we're going to look at the electronegativity difference of oxygen and hydrogen. Let's look at the oxygen. Oxygen is here, right? You see it, the number 344, and the hydrogen is 2.2. So 344 minus 2.2, it'll be 124. Because it is less than 1.8, so less than 1.8, it is covalent bond. But because it is more than 0.5, it is gonna be polar covalent bond. And the way it happens that hydrogen shares electron, oxygen shares, hydrogen share, and oxygen share. So now look at the number of electrons around oxygen. I got 1, 2, 3, 4, 5, 6, 7, 8. Octet rule completed. Okay, so stability gained, stable. And then hydrogen cannot have more than 2 electrons around it because it's a first group element. So for hydrogen, the stability is not the octet rule. It's just 2 electrons because hydrogen is a first period elements. You see here, hydrogen here. Hydrogen can only have 2 electrons. 2 electrons. So once hydrogen completes the 2 electrons, hydrogen is stable. Okay, so this is how the covalent bonding happened. Now we're going to do Lewis dot cross diagram for hydrogen. Hydrogen have 1 and the other one has hydrogen. We're doing it for H2. They share with each other. They share electron with each other. Look what it happens when they share electrons. Let's count the number. I got 1, 2. And I told you hydrogen can only have 2 electrons. So because it only has 1 shell. And first shell can have only 2 electrons in it. Maximum 2 electrons max. So they share electron and they become stable. And then once they share, so each 2 electrons equals to 1 bond. 1 bond. They shared the electron, they made this 1 bond in here. Okay, so form the single. Now let's look at the chlorine. So normally they should have done a dot cross, but they only did cross on this guy. So if we do a dot, it's going to be a 1 dot here, 1 dot here, like this. Okay, and this is cross. Chlorine got 17 electrons. We have done this is 1s2, 2s2, 2p6, 3s2, and 3p5. So we include only the last shell, which is 7 electrons. That's why I put 7 in here and 7 in here. Now these guys, they are gonna share it because chlor2 electronegativity difference is gonna be 0 because chlorine, they're the same elements, right? When you deduct what is the electronegativity of chlorine, it is 3.16. So 3.16 minus 3.16 will be 0. So it is non-polar covalent bond. Okay, so now they're gonna share the electron. So this guy is dot, 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 dot. Now they shared. So now let's count the number of electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They have octet rule completed. So they reached stability and they made a bond. Because we have 2 electrons here, so 1 and 2, it looks like this: chlorine, chlorine. Okay, just like this. This spare electrons, I put them in here. But this is my Lewis dot cross diagram. Dot cross diagram. So now we're going to do oxygen. Oxygen got 8 electrons, 8 atomic number, which means 8 electrons. It is 1s2, 2s2, 2p4. First shell we got 2, last shell we got 6. So now look here, I got 1, 2, 3, 4, 5, 6. And then on this oxygen, I got 1, 2, 3, 4, 5, 6. We know that the inert oxygen is also diatomic, meaning I need to have 2 oxygens. The electronegativity difference is going to be 0 again, because oxygen in here, we got what? 344 for oxygen electronegativity. So 344 minus 344, it'll be 0. It is the same element. So it is non-polar covalent. Okay, so now look at this guy. He shares 1 electron, this guy shares 1 electron. But when you share the first 2, it's not enough. Because when I share the first one, it looks like this. So I got, you see this here? So I got 1, and then another cross. And then how many electrons do I have here? 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. Now let's count the number of electrons. So 1, 2, 3, 4, 5, 6, 7. 7. It's not octet completed. So I need to share 1 more, and then this guy needs to share 1 more. So when they share 1 more, you see they each shared 2 now. Now let's count the electrons that they have. So it is 1, 2, 3, 4, 5, 6, 7, 8. Now I got octet on this oxygen. Let's count this guy. 1, 2, 3, 4, 5, 6, 7, 8. You see, these electrons are shared. So that's why they have the octet rule. Now, I told you each pair of electrons equals to 1 bond, right? So because I have 4 electrons shared, I have 2 bonds. Okay, 2 bonds in here. You see, they shared 2 electrons each. This is how it looks like. 4 electrons here. So this is my Lewis cross dot diagram. This is the one. Okay. But if you want to write the bonds, you write like this. This, and then the other 4 electrons are on top of. So formed double covalent bond. Now let's look at nitrogen. Nitrogen, we're going to do it together. I have 1s2, 2s2, 2p3. Nitrogen got 7 atomic number. So first shell 2, second shell I got 5. So I have nitrogen, and then I'm gonna put 1, 2, 3, 4, 5. I showed my last shell on the nitrogen. I didn't show the first shell. And then the other nitrogen I got here. Now I have 1, 2, 3, 4, 5. So now when I share 1 electron and this guy shares 1 electron, we have here like this, and then 1 like this. But if you check this out, so when I count the number of electrons in the first time, when I share 1 on each, it'll be 1, 2, 3, 4, 5, 6. I'm gonna prove you how. So nitrogen here, sorry. So I got nitrogen, right? And then this nitrogen. This is one, and this is the other one. So now if I put 1, 2, 3, 4, I got 5 in here, and then from this guy I got 1, 2, 3, 4. Now let's count the number of electrons around this nitrogen. 1, 2, 3, 4, 5, 6. 6 electrons. It's not enough. It's not octet. I need to have 8. So what I do, I get one more electron. I share one more here, one more from this side, and one more from this side. Sorry, I meant to write this guys in cross. So one from this side. And what happens the next is that I get now nitrogen is gonna be so looking like this. Now I have 1, 2, 3. I got 1, 2, and then 3, 4. So I got 1, 2, 3. So now let's count the number of electrons. So I got 1, 2, 3, 4, 5, 6, 7. 7. It's not enough. So I share one more electron. So this guy shares 1, this guy shares 1. Now see what happens here. This is the scenario. I got left with 2 electrons, which is in this case 2 electrons on each side, but I have 1, 2, 3, 4, 5, 6 electrons. Now let's count the number of electrons. This is 1, 2, and then I have 3, 4, 5, 6, 7, 8. So altogether octet rule completed. But I have 6 electrons that I shared. 6 electrons means 3 bonds. 3 bonds. Okay, there's 3 bonds. So this is how it looks like. Nitrogen, 1, 2, 3 with the other nitrogen, and I have 2 electrons. And Lewis crosstalk diagram is this. Okay, so when we ask you guys to write the Lewis dot cross or crosstalk diagram, this is what we're asking for. Nitrogen gotta be looking like here, and then here like this. So I would be 1, 2, and then 1. Sorry, 1, 2. So 1, 2, 3, 4, 5, 6. This is the Lewis dot and cross diagram. Okay, so now we have done this. We got chlorine, oxygen, and nitrogen. So the same thing for hydrochloric acid. We got hydrogen and chlorine. We got 1 bond, 2 bonds, and 3 bonds. I want to remind you that the first bond is always going to be a sigma bond. It is stronger bond. Stronger than pi. Now the second bonds are going to be pi. Because I don't have a second bond here, I have no pi bonds. But for oxygen, if you look, I got 1 and 2. So this one is sigma and this one is pi. And then we have here, this one is going to be sigma and this one are going to be pi. So it could be even this one is sigma. It doesn't matter. It just, you need to understand that if you have a three bonds, one is going to be sigma, the other ones are going to be pi. Okay, sigma and pi bonds. Now let's do the CH4 methane Lewis dot cross diagram. Okay, so now look at here. Carbon has 6 electrons, 1s2, 2s2, 2p2. Last shell, I got 4 electrons. So I put 1, 2, 3, 4 on it. These are cross. And then hydrogen got 1 electron. So I'm going to put 1, 1 on each one because I got over here 4 hydrogens, you see. So now each hydrogen and carbon share one. They share. Okay, they share. Look what happens. Now they shared. Now let's count the number of electrons around carbon. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so octet rule completed. Hydrogen, I told you that it can have a maximum 2 electrons. So that's how it achieved its stability. It's not octet, it's the hydrogen stability. It's not octet. Octa means you need to have 8. So this is the Lewis crossdot diagram of CH4. So I'm just going to delete it so you guys can have the final picture. Now I want to compare the nature of this guy. So carbon. If we go back into here, carbon has 255 for electronegativity, and hydrogen is 2.2. So 255. So electronegativity difference is 255 minus 2.2. It is 0.35. Because it is less than 0.5, but more than 0.35. This guy is non-polar covalent. Okay, non-polar covalent. And I told you that each pair of electrons is one bond. So one bond, that's why I have here 1, 2, 3, 4 bonds. Okay, 4 bonds on methane. And we have constructed the model with you guys. So now polar covalent. I forgot to look at the nitrogen in here. Nitrogen is 3.04 and hydrogen is 2.2. So if you do the math, so 3.04 minus 2.2 electronegativity difference between nitrogen and hydrogen, this will be 0.84. Because it is more than 0.5, this is polar covalent. Okay, so polar covalent. So nitrogen is 7, 1s2, 2s2, 2p3. They are drawing the Lewis dot cross diagram here. I got 5 electrons in the last shell, so they put nitrogen here. 1, 2, 3, 4, 5. And then hydrogen is 1 electron, so they put 1, and they each share electron. Okay, so this shares and they share electron. This is how it looks like. These are shared electrons. Hydrogen got stability because it needed 2 electrons. Nitrogen, let's count it. I got 1, 2, 3, 4, 5, 6, 7, 8. So 8 octet rule achieved. Okay, so, and this is how it looks like. Nitrogen with 2 electrons that we didn't use, and then hydrogen, and hydrogen. Now we're gonna do the group work that we had on the slides. We have already done NH3 ammonia up here, and then we're gonna do ethene, and then we'll do ethanol. So carbon, we said that it has 4 electrons, right? So we will draw carbon with the last shell, and then we have another carbon with the last shell, and then I have hydrogen, right? So hydrogen, we know that we only have 1 electron, so we'll have hydrogen, and hydrogen. Ethene is C2H4. So last shell electrons, we got 1, 2, 3, 4 on carbon, and then hydrogen has 1. Okay, we're doing Lewis dot cross diagram. So currently this electron with hydrogen and carbon, they get shared, and this one get shared, and then we have the same thing over here, one with this one. And look at here, now I have 2 electrons. If I share 1 electron from each one, let's count the number of electrons around carbon. So around this carbon I got 1 electron that he didn't share yet, but I have 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6. So altogether it adds up to 7. Same thing in here. I have the shared electrons that I have. So that's why I'm gonna do 1 more electron that I will share with this carbon, because hydrogen can only have 2 electrons max. So if I share those electrons, this is how it's gonna look like. So I got carbon, and then another carbon that I shared. Actually, I'll do this, and I'm just gonna draw the carbon in the center, and I have this one, this one, this one, and these are hydrogens. And if you look at here, I have 1 hydrogen that 1 electron that hydrogen shared, 1 is coming from carbon, and then I have here 1, 2, 3, 4, and then now let's count the number of electrons around carbon. I have 1, 2, 3, 4, 5, 6, 7, 8, which means I have 8 electrons. The same thing around this carbon, and around hydrogen we have 2 electrons. So altogether, because I shared 4 electrons, it means I got 2 bonds, right? So this one looks like this: carbon, double bond, and then each bond is like this. So this is how it looks like, and Lewis dot cross diagram is here. Now I'm gonna do ethanol, which is C2H5OH. We know that carbon has 4 electrons in the last shell. I got 2 carbons, 1, 2, 3, 4, and then 1, 2, 3, 4. Oxygen has 1. I'm gonna do cross on oxygen. 1, 2, 3, 4, 5, and 6. If you look at it, it's 1s2, 2s2, 2p4. So I got 6 electron in here. And then hydrogens are, I got I got 6 hydrogens. I have 6 hydrogens, and I'm gonna write them with the green one, green dots. So 6 hydrogens, and now I will connect all of them together. So carbon and this carbon, they come here and they share electrons with each other. Actually, I will do it like this. So carbon, and then this carbon. Okay, so this is here, and then this carbon is here, and then oxygen, I'm gonna draw it here, and then I have 1 hydrogen here, and another hydrogen will be here, another hydrogen will be here, and the other hydrogen is here, it's gonna be here. Now that I put my elements, let's put my electrons around it. So carbon has 4 electrons. You see, I put 1, 2, 3, and 4. And then the other carbon has 1, 2, 3, and 4. Oxygen got 6. So I put 1, 2, 3, 4, and then I share each one with the neighboring element. Okay, and then I put the hydrogens, electrons, which is going to be 1, 1, 1, 1, 1, and then 1. Just like so. So if you now count the number of electrons around carbon, you would see that, for example, this carbon, I have 1 electron here. I got 1 here, 1, 2, 3, 4, 5, 6, 7, and 8. 8 electrons. So each carbon is like this. They got 8 electrons, and then oxygen, you check, you're gonna see that you have 8 electrons. It happened because they share the electrons. And this is the Lewis dot cross diagram. And we said that each 2 electrons is 1 bond. So I'm just gonna draw you the shape. So I got carbon, carbon, oxygen, and then hydrogen, and then I have hydrogen, 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 and hydrogen. This is how it looks like, but the Lewis dot cross diagram is this one here. Okay, so thank you very much, guys. I think it should be all clear now.